So here I take a look at the Hall Heroult Cell, the extraction of aluminium from bauxite. First of all, this is what bauxite looks like, and you can see from its appearance it isn't pure aluminium oxide or alumina, which is white. It contains various compounds of iron and indeed other compounds as well. But this chemical, alumina, aluminium oxide, a white powder, can be extracted from bauxite. Here's another ore of aluminium. It's called cryolite, formula Na3Alf6. It's added to the Hall cell to lower the melting point of the alumina, lowering the melting point from well over 2000 to under 1000 degrees C. So remember, the cryolite lowers the melting point of the melt or electrolyte, greatly reducing the cost. This picture from Lough in the south of Ireland shows the impurity that is left when alumina is extracted from bauxite. Bauxite typically has small amounts of other compounds. Iron 3 oxide is present, giving the red-brown colour. Also present in the bauxite are silicates or clays. And you're also likely to get titanium oxide and other minerals as well. A quick look then at the chemical extraction of alumina from bauxite. Aluminium, unlike iron, is amphoteric, so alkali is added, making the alumina go into solution. The iron and other metal salts remain solid and are filtered off. The aluminium salt solution is then acidified, producing insoluble aluminium hydroxide, which is heated to produce alumina, aluminium oxide. That's a quick run through the chemical process to obtain pure alumina from bauxite. Having extracted the alumina from the bauxite, the alumina is then transported from Lough in the south of Ireland, around the south coast of Ireland, and over to Anglesey in Wales, where electricity is produced more cheaply. And remember, the Hall Heroult cell requires vast quantities of electrical energy. Okay, so here's what the Hall cell looks like. It's a steel tank lined with graphite, which becomes the cathode. But first there you see the anodes have been labelled, and they're made from a mixture of pitch and coke. The anodes attract oxide ions from the aluminium oxide in the electrolyte. I've labelled there the steel tank, which is then lined with graphite, and the graphite becomes the cathode, the negative electrode. So a steel tank lined with graphite that becomes the cathode, and then dipping into that the anodes made of pitch and coke. The graphite lining, charged negatively, attracts the Al3+ ions in the electrolyte. You can see there's a cover there over the anodes which can be removed in order to replace the anodes, as is necessary every couple of weeks. And there's a vent there to allow the gases to escape. And the exhaust gases you see there are carbon monoxide and carbon dioxide. That horizontal beam is used to enable lowering of the anodes into the electrolyte as it wears away. You can see a crust of frozen electrolyte. The crust helps to keep the heat in, which again lowers the cost, the running costs. But the crust needs to be broken to add more alumina periodically. Note that this is a continuous process and not a batch process. Continuous process is cheaper. Continuous because once up and running, it isn't stopped. You simply put more of the alumina in at the top, having broken your way through the crust, and then you tap off the aluminium at the bottom right there. A batch process where you start and stop is less efficient, wastes more energy. Okay, now let's focus in here, highlighted in yellow, so that we can see what's happening in terms of the ions, how they are discharged at the electrodes. So I'm going to stretch this part of the cell out. There's the anode dipping into the electrolyte through the black horizontal line representing the crust on top of the electrolyte. Now, if you can run this video in your mind, it'll help you remember the process that takes place, or processes. So let's pick up on the details of what's going on here, including the redox chemistry. The aluminium ions at the top left here, in what's called a half equation, are shown to gain 3 electrons and form atoms. Remember the mnemonic oil rig: oxidation is loss, reduction is gain. So the aluminium is gaining electrons and is reduced. The oxide ions change into oxygen atoms and electrons. So the oxide ions are giving up electrons, and that is oxidation. The oxygen formed at the anode reacts with the carbon anode, forming oxides of carbon. So unfortunately, the anodes wear away and have to be replaced. Look at the green spheres there with double minus charges. Those are the oxide ions arriving in, giving up 1, giving up 2 electrons, and changing into oxygen atoms, which you can see combining with the carbon atoms of the anode to form either CO or CO2. So oxides of carbon are being produced there. But the important thing is they are leaving electrons at the anode, and those electrons move around through the circuit in an anti-clockwise direction to be picked up by the aluminium ions, the Al3 plus ions, as they arrive at the lining. And that produces aluminium, which builds up as molten aluminium, and it's tapped off periodically at the bottom right. And if you look at the bottom of the Hall cell, you'll see pink spheres with 3 plus charges. They represent the Al3 plus ions. They're attracted into the negative cathode, pick up 1, pick up 2, pick up 3 electrons each, and are changed into the element aluminium, or atoms of aluminium. And when enough aluminium has been produced in the Hall cell, it gets tapped off there at the bottom right, or sometimes a lance is used to draw out the aluminium in a siphon effect. And you can see the crust is broken periodically to put in more alumina at the top. That makes it a continuous process and not a batch process. Again, a continuous process wastes less energy and is more efficient. So there you have it, the Hall Heroult cell, used to electrolytically extract aluminium from alumina, aluminium oxide, which is extracted chemically from the ore of aluminium called bauxite. Thanks for listening. Hope you found that helpful.